If it's false, I'm going to put in a 0. And if it's true, I'm going to create a constant and put in a 0.8. So if you had a simple robot that all you needed to do was turn on a third motor with a ball picker-upper, I'm sure that's not a real term, but I just coined it. When you push the button and turns it on, you're done. You deploy this code, it will run on the robot, and you're ready to go. So the intention of this demonstration was not to explain all the bits and pieces. There's no way I could do that in 10 minutes. In fact, I went over my prescribed 10 minutes. The goal was just to give you a flavor for how we set things up, how we do things in LabVIEW. It may look a little bit cartoonish. I've heard that phrase before. But in reality, once you see a lot of the fundamental structures behind how you do things in LabVIEW, you see that it's actually very powerful. And most of the key fundamental programming structures are there in an almost identical way. You just have to look at them a little bit differently. Are there any questions about what I've done so far? I skipped the turn on and autonomous mode. I'll come back to that later if there's some interest. But I went a little bit over my time limit. So, as far as deciding which is a better environment to use, or what information you need to gather to make the decision, you have to check how well it works, right? So which is easier to discover or adapt? So we opened the example code, right? We're given example code which accesses the libraries, whether we're using C++ or LabVIEW, right? Which is easier for the students who are evaluating it to make changes, to add functionality, to modify the existing functionality. I made this comment in the presentation, but most functions operate just like this previous demo. This idea of opening something, talking to it, and later closing it. Whether you're doing a motor like we did, or whether you're doing an additional joystick, or whether you're reading from an accelerometer, or whether you're talking to an encoder. The block names are just different, and the wire contents are just different, but the fundamental approach is the same. So talking a little bit about the skill set of the team. So it's important to say, depending on where they start, where is it most natural to go? I'm just going to skip forward to see the graphic here. So what I've shown in the 3 yellow blocks here are a progression through the first robotic programming life cycle. You start in FLL, you move on to FTC, and then you go on to FRC. So in FLL, you've got 2 choices. You can use NXTG or RoboLab. In FTC, you've got 3 choices. NXTG or LabVIEW or RobotC. So based on talking to a lot of people with a lot of experience in this, going down both streams, there tends to be a more comfortable progression. And I've shown that with these arrows. So the 2 turquoise boxes are showing classroom curriculum. So if you start off learning Java or C before you come to the first world, you're probably not going to go right into FLL. You're probably going to go right into FTC, maybe even FRC. So it's a little bit more natural for programmers who have already learned Java or C to learn RobotC. That is a natural progression. Or to jump into Wind River or C++. If you started with a more high level, like Alice or Turing, or you've started using NXTG in high school or in public school, in advance of that, then it's a more natural gravitation to go back into NXTG when you're doing the FTC program. NXTG flows very naturally into LabVIEW. They're the same basic approach, which is data flow programming. It's a graphical in nature. So students who have seen NXTG, it's not that it's an easy transition. There's definitely a learning curve there. But it's a natural transition from NXTG into LabVIEW. And of course, the flow into FRC, if you've used LabVIEW or you've used NXTG, then LabVIEW is a more natural choice for programmers for the FRC competition. Also, I've talked to a lot of people who made the comment that in curriculum, in juniors and for sophomores in high school, the programming you do tends to be less and less, in a lot of schools, based on the traditional programming languages. Less and less Java, less and less C. And Alice is one, which wasn't even on my radar, which I hadn't heard of previously, which is something that's a kind of a somewhat graphical, high-level language where you're not so much focused on the fundamental control of data like you are in C. You don't have to dimension arrays or anything like that. And that is the kind of environment which also tends to flow somewhat naturally into the NXTG or the LabVIEW approach. Okay, so the next point of evaluation is performing this comparison test. So sit down and write some code. If it's 2010, take your 2009 robot and reprogram it in C++ and compare it. Or reprogram it in LabVIEW and compare it. Or even better, take your 2008 robot and transplant a controller into it. Many teams already did that this year because we had our new C-Rio controller this year. Took it and put it in this 2008 in the preliminary time before the build season to be able to test out this controller, to be able to test out how to hook it up and how to program it. So do that. Do that and try both environments and see which is more natural and a more appropriate choice for your students. And then, and this was suggested to me by an awful lot of people, and I believe very strongly about this, train on both. A lot of teams have the benefit of having a whole bunch of students. And what usually happens is we get a couple programmers, sometimes by the end of the season it's just one programmer who becomes a specialist. And unfortunately, that person, he or she, is very often a senior and leaves, fortunately for them, unfortunately for us, goes on to college to a great and wonderful career, maybe comes back as a mentor in 5 years, but we've lost that skill set. So it's really nice to train on both. We have the benefit of being given thousands and thousands of dollars worth of software for us to use for free. If we have bodies and minds, even more importantly, that are willing to try this stuff, let them work on both. Set up a bit of a competition. See who can get things going faster. See who has the better idea. Let them work together. Let them compete. Do all of these ideas to take advantage of this time and these great tools we have. It's a nice opportunity to learn in context. I mean, as an instructor myself, it's a rare treat to be able to talk about programming and making things go and have someone actually have hardware that goes. We spend a lot of time teaching people how to program. What is a while loop and doing kind of abstract things. Here's a great opportunity to implement a state machine or some structure like that and actually watch it move across the floor. So this is a great opportunity to learn in context, and we should take full advantage of it. So, what I'd like to point out now are some of the key differences between LabVIEW and C++. The environment is obviously one. We saw that, it's graphical, there's very little typing, navigating doesn't involve accessing subroutines the same way you do in the C++ environment. Parallelism and multi-threading. LabVIEW has a neat side effect of the data flow paradigm, which is if two things don't have a wire connecting them to each other, they run at the same time. So that means if you want to start motor A and start motor B, they'll start at the same time. That means if you have a whole loop which is involved in your steering, and a whole loop involved in your propulsion or your drive system, and there's no wire between them, they run completely in parallel. And in advanced deployments, they actually run in different threads. So that's not necessarily so much the case. We don't have to worry about that for the C-Rio. But in my business, and when I do a lot of programming in some of the more advanced deployments using LabVIEW, it's tremendously powerful to be able to have your vision system working over here and your drive and propulsion working over here, but it's the same processor, they're just in different threads. And it's literally a case of selecting which thread you want to run in. So that's something that is somewhat more difficult to achieve in C++. Debugging. For those of you who have used the LabVIEW environment, you know that you can probe your code while it's running via your host computer. That's something that's a lot more difficult to achieve on C++. If you're going to debug and keep track of how your program is doing, you have to use the console output, which kind of requires being hardwired or tethered to something. Or some of the teams have done some really advanced stuff with debugging by using digital outputs to encode states of things. So it's absolutely possible to do it, but in my personal opinion, it's more natural within the LabVIEW environment to debug. Machine vision. A lot of people who have done testing with machine vision, who have implemented cameras for their ball or their opponent tracking systems for the FRC competition, If you're using the LabVIEW-based tools for vision, you have the ability to do a lot of prototyping with graphical feedback. So you can see the image, you can see the results of the tool on the screen. And that's a very powerful thing. From my understanding, using C++, you get a live feed from the camera via an HTML page, but you don't get to see the results of your tools being applied. You have to kind of monitor that in a separate way.